So let's continue our example. This time I want to bring in initial conditions, and then I'll be able to think about what a certain particular trajectory looks like. So this is all still based on that same homework problem, problem 11, which does contain some specific initial conditions that I could try to play with, but I think it's more fun to think about the general problem, solve that, and then go plug in the specific thing being asked for here. So let's say you're given some initial conditions, x of 0 equals x naught. And these x's have vector symbols on them. That's telling you that really it's two initial conditions, right? It's like x of 0, y of 0 equals x naught, y naught, right? So that's, in this example, it's x naught is 0 and y naught is 1. And the vector symbol version of x naught is the vector 0, 1. Yeah, so let's say you've got x of 0 equals x naught. Then I just want to impose this equation and then see if I can solve for C1 and C2. Now let's see if I can use some linear algebra to make this not turn into a giant mess. So I have three choices for how I want to group the terms in my general solution. So to remind you, these were my x1 and x2, some green thing here and some blue thing here. I can write c1x1 plus c2x2. I can write it like this, grouping it by these vectors. I can write it like this, grouping it by cosine parts and sine parts. Let me think about this. Okay, I thought about it. I think I like the original way of writing it, this first way here, the most. So yeah, in order to work out the left-hand side, it'll be nice to know what is the green x of 0 and what is the blue x of 0. So x1 of 0 is going to be there's too much stuff on the screen. Okay, here's x1 up here. If I plug in 0, I get 1 for this exponential, so it's just not doing anything. And then this is 1, and this thing is just 0, because the sine of 0 is 0. So I just get the vector 4 minus 2. 4, negative 2, I mean. Oh, well, that's nice. And then how about x2 of 0? Scroll back up. Here's x2. I get 1 times negative 2, 0. And then that part is 0. So I just get negative 2, 0. Great. Now I can write down what is this initial condition. It's saying x of 0. Okay, let me scroll back. This is x in terms of x1 and x2 is up here. So this initial condition is saying x of 0, which is c1 for negative 2, right? c1 x1 of 0 plus c2 x2 of 0. So that's the left-hand side, x of 0. c1 x1 of 0 plus c2 x2 of 0 equals x naught. All right, there we go. That's a linear algebra problem. That's something I can plug into a computer and easily have it solve. It's this matrix times the vector c1, c2 equals the vector x naught, right? So then how do I find out what are c1 and c2? Well, quick and easy way is invert the matrix. And even if you're not plugging things into a computer, this still saves you algebra steps. Because inverting this matrix, I mean, there's a formula for inverting a 2x2 matrix. So it does save you from some amount of thinking. Okay, let me spell out what the vector x naught is. It's x naught, y naught. And I'm sorry, I forgot the inverse symbol. That was the whole point. So I need to invert this matrix. All right, well, you can do this with Mathematica or with Wolfram Alpha. Just ask it for the inverse. You can basically just type what I'm typing here in Wolfram Alpha. That should work. Just ask for the inverse of this matrix here, 4, negative 2, negative 2, 0. Negative 2, 0. And looks like it's that. And if I do this, I can make it look pretty. 0, negative 1/2, negative 1/2, negative 1. Great, so now I've solved for C1 and C2, right? In terms of the initial conditions. I know that C1 is negative 1/2 x naught, and C2 is negative 1/2 x naught minus y naught. All right, now I can go to the stupid WebWork problem and see what it wants from me. It just wants me to put in 0 for my x naught and 1 for my y naught. So basically put the vector 0, 1 in here, or just stick in 0 for x naught and 1 for y naught. Then I get C1 equals 0, C2 equals negative 1. So when x naught equals 0, y naught equals 1. That's what it was, right? Yep. C1 equals 0. Wait a second. Mistake here. C1 is negative 1/2 y naught. The negative 1/2 is here, not here. That's my bad. Yeah, so C1 should end up being negative 1/2 times 1, and then C2 would be negative 1. And now let me scroll up and write down the specific solution coming out of my general solution. And my favorite way to do it is still is going to be this one, I think. I think I like this one. Okay, so I've copied it over. This is my general solution, and now I'm going to fill in the C1 and C2 that I got. So there, I have filled them in, these C1 and C2, to get me these initial conditions in the problem. I filled them in here for where C1 and C2 were, and now I have a specific solution. I can simplify this though, and I think I would like to. I can write this vector, this here that you're looking at is a constant vector, and this is just some constant vector. Why not just simplify that? All right, there it is after one step of simplification, and then let me just add these pairs of vectors here. There it is after more simplification, and I can probably write this, just make it look prettier. So let me just go ahead and rewrite it. X of t is an overall e to the minus t, and then I've got the vector 0, 1 times cosine 2t plus minus 6, 2 times sine 2t. And you see, when I'm making my phase diagram, these two vectors, 0, 1 and minus 6, 2, those are like what I was calling A and B, the vectors that before the distortion into an elliptical shape, those vectors were pointing to the east and the north poles of a circle, of a unit circle. Okay, and now I'm pretty terrified that I have done something wrong. There are so many places I could have made a mistake. So let's pull this up in Mathematica and just check that we actually satisfy the differential equation and the initial conditions. Okay, so let me be honest with you. I was scared that I got something wrong way back when I just had the differential equation, so I already checked it. So I am certain that this part is good. So I guess what's left is I checked it off screen. But what I haven't checked yet is that I got the initial conditions correctly. So let me type in x is e to the minus t, and I'm going to type in this specific solution that I got. Let's see. In parentheses, and then it's some vector that I'm going to write down, times cosine 2t plus some vector times sine 2t. The first vector is 0, 1. The second vector is negative 6, 2. And then two things to check. Does it satisfy the differential equation, and does it meet the initial conditions? So the differential equation was that x prime of t should be a matrix applied to x of t. X prime of t is this big stuff. And then I'm wondering, is this equal to, and then a certain matrix, certain 2 by 2 matrix times x of t. This dot does matrix multiplication in Mathematica. And what was the matrix? It was -5, -10, 2, 3. 2, 3. Okay, so I wrote this double equal sign to just write an equation rather than doing an assignment. And it says, yeah, this equation is equivalent to this one that I just spewed out at you. But I don't want to eyeball these terms and see if it works. So I can actually simplify and see what it thinks. Oh, it thinks that my equality is true if and only if that equals 0, and that does not look like it equals 0. I made a mistake somewhere. Yep, I'm glad I did that check. Apparently I'm not able to do arithmetic, so when I was simplifying the vector that was here, it was not -6, it was -5. I'm not sure what I did wrong there, but that seems to be the problem. So this is a -5. And now if I fix this and I put -5 there instead, please say true. Yes. Okay. So this equation is true. X prime really is matrix of coefficients times x. Right. And the initial conditions. So is x of 0 really 0, 1? Yes. Very good. That was the goal, right? To get x naught 0 and y naught 1. So now if I want to go and type this into WebWork, I have to give the x of t and y of t separately, which sometimes is what you actually want. And only now do I finally break apart this vector into 2 component functions, right? So my x of t will be e to the minus t times 0 cosine 2t plus -5 sine 2t. And my y component will be e to the minus t times 1 cosine 2t plus 2 sine 2t. So only at this stage would I break it apart and put it in here. And I've already answered this question. It was a stable spiral, right? I already knew that before looking at any particular solution. Okay, but I think it would be fun, now that we have some specific one, to try and draw what this looks like. So we've got the vector 0, 1 here. So let me plot that. Let's say that's, okay, let me make it look kind of short. Since that one looks like a pretty long vector. -5, 2, so -5, 2, so like that. And what does this trajectory look like? Well, at time 0, it's here, right? And then at whatever time puts me at pi over 2 radians, so time 1/2 actually puts me at, or no, time pi over 4 would put me at pi over 2 radians in here. That's when I'd be here. That's when cosine 2t, when time is pi over 4, that's when cosine 2t becomes 0 and sine 2t becomes 1, so I end up here. So that's a portion of what's happening. And then another pi over 2 radians later, however many units of time that is, I end up at negative of this vector, so 0, -1. And then another pi over 2 radians later, I end up at the negative of the other vector, 5, -2. Then another pi over 2 radians later, I circle back. You can see the direction of travel here. Okay, actually, I have not plotted the trajectory yet. I've plotted this trajectory of this without the e to the minus t, right? So I find it easier to think about that first and then slap on the e to the minus t. Okay, so now play the same animation, but while this looping around is playing, also overall decay towards the origin. So then what does that look like? Oh, let's do that in yellow. That would look like something like that. So spiraling in, and the spirals just get really small really quickly because this is exponential decay. Okay, let's plot it in Mathematica, actually. So this is the same Mathematica notebook that I used in the previous lecture. And all I've changed is I put in our new general solution up here. So what I typed here is this, our general solution. I just chose to write it in this form. Scratch that. I chose to write it in this form. Anyway, I typed in the general solution. So it has these unknown C1 and C2 showing up. And I want to play an animation of this solution that I think looks like this yellow spiral. So I've got this thing here that lets me choose C1 and C2. So let me choose C1 to be -1/2, -1. And let me set the plot range to be something reasonable so that we can see these different vectors. Actually, I think it already is reasonable. Let me just extend the time here so that let's make it do one full loop. So, okay, this would be fun. Let's see if we can predict the period. How long will it take to go around and come back once? Of course, it's not actually going to come back since it's decaying as it goes, but how much is 2 pi radians? How much time? Pi units of time, right? If you increase t by pi, then you increase the number of radians you're putting in here by 2 pi. So let's run from 0 to pi. And watch that. There it is. And actually the parametric plot is not running from 0 to pi. There. That's one loop around. Let's let it do 2 loops around. So 2 pi, that's 2 periods for this thing because it has an angular frequency of 2. And now it can do 2 loops around. There's one, now it's doing the other one, and the other one's really tiny. So you see that's spiraling in. And if I remove this exponential factor here, then I want to expand my plot range. I think instead of this, I can just put one number, like 5. There. You can see it goes around an ellipse, and it's still doing it twice. So all we're doing is putting exp minus t here. Now it's like that. And finally, if you want to run that same code from last time that shows you a bunch of solutions, it's this. Oh, I need to this is using the variables C1 and C2. Yeah, I just needed to clear out C1 and C2. So there you go. There's a family of spiraling in solutions, and they're all, no matter where you start, no matter what your initial conditions are, you end up going along some spiral in towards the origin. So this is the origin here is a stable equilibrium. And you can see if I remove this exponential factor here, then you get just ellipses around the origin. So when would this happen? When would you not have that exponential factor? That happens when you actually have purely imaginary eigenvalues. So up here in our calculation, if our real part was 0 and our eigenvalue is purely imaginary, just something times I, so just 2i, then this exponential part is just e to the 2it there, right? And then what goes here is just 1. This factor is just not there. So you don't have that overall exponential factor, and then you have sort of orbiting around the origin. This was the situation that we referred to earlier as the origin being a stable but not asymptotically stable critical point. So like if you perturb away from the origin, then you don't run off, you don't run away no matter which direction you perturb away from the origin, you never run away. So it's not like an unstable equilibrium, but you also don't go back either. You just continue happily orbiting the origin. So this situation, this would be called a stable center, which is not what problem 11 is, but that situation where you have purely imaginary eigenvalues and no exponential decay or growth, that's a stable center. So solutions tend to look like that. And even ones that are tight and close to the origin will still not decay to the origin or run away. They just circle around. That's a stable center.